Yeah, so like I said before, this is sort of a beginner, for some definition of beginner talk, in that I'm actually going to be going over like, what is a law? At least how do I think about it? Why do you care? Why do you care that you have associativity? What is associativity, etc. So if you're already really comfortable with that, you might be. Oh, thank you. And oops. And I do have a lot to cover, so I'm going to go probably to the end. OK. Yeah, just let me know whenever you're ready.
I'm just going to go ahead and start because I'm ready for stuff. But
OK.
Sounds good, so you'll hear you and listen to me.
OK. Cool. So let's start. OK. So we're going to talk about what I call abstract algebra-driven design, as you can see. Cool. We'll just wait. And specifically, we're going to use animations to help sort of motivate I guess, this like abstract notion of like designing APIs. And so this is an animation, OK? So why don't we start here? OK, so let's look at this, right? Really, we have two things kind of going on. OK, so we fade in. We have something on the left that's growing. We have a thing on the right that's rotating, right? So if we think about how we might describe this, the thing on the left, we're like growing some view from some radius to another, and that's making the text grow. And specifically, this is done with what's called an ease in out curve, which in animation, it's like you start off a little bit slower, and then you speed up and slow down. And this sort of reflects natural motion, so we like to do this in our animations. On the right, we have this other view that rotates, and this one had a high ease out. Maybe you didn't notice, but it did. But really, the animation is both of those animations running at the same time, and really, it fades in first, and then all the animations run, right? So I guess this is kind of how I would imagine we could describe the animation. And just as like a sneak peek, this is what the code actually looks like in Swift, in the library that I made. I'm not going to describe exactly what's going on here now, because I guess we're going to get to it later. But the point is you can build something that kind of looks like the natural description. So OK, don't worry about the specifics here. But if we take a step back and just think about designing libraries, right? If we want a good library, it should have these two properties. OK? We want to minimize complexity, and at the same time, maximize expressivity. And I'll go into more detail. I think you can measure these things. I think you can measure complexity by counting the number of public interface primitives, which is a term I made up. But really what I mean is a type, a method, a function, a parameter, a hidden state, an error code, anything that you have to think about when you're interacting with some interface, be it documented or not. And so the more of these things you have to think about, the more complex you sort of have in a library. And then expressivity is this notion, some people have their own definitions, whatever. I say if the number of ways to solve problems goes up, then you have a system that is more expressive. I don't care if it's the same problem that you're solving. If you can solve it in more ways and give choice to the consumers of your API, then I would say it's more expressive. And this is sort of like a nice property to have, I think. And that sort of leads you to this trade-off. Let's look at the green line. I think this is what happens if you aren't careful. So on the y-axis, we have complexity. On the x-axis, we have expressivity. And so what the green line is saying is, as we try and make our library more expressive and do all the things that we would want our library to do, such as animate things, if we're not careful, we can just end up adding a ton of methods that maybe do a ton of side effects. And we end up with something that's really complex and hard to use, in my opinion. But if you're really careful, then you can end up with this red line instead, I'm going to argue. That eventually goes up to infinity as well. But for a while, we sort of get expressivity for free without increasing complexity. And I think this is kind of cool. So, OK, this is all very abstract. Let's think about animations again. And really, I guess this maybe applies to other libraries as well. But we should look at what's out there, OK? I've done a bunch of work in native apps. So we're going to look at iOS and Android, OK? So iOS, this is Swift code. There's this animate method that's on all UI views. And really, every view, anything you see, is a subclass of UI view. So it has this animate method. Animate is overloaded hundreds and hundreds of times. Maybe I'm exaggerating, but it's quite crazy. This is one of those overloads. We have a with duration. You can pass a duration. There's an overload where you can change the easing curves, and et cetera. And then we have this animate callback. And in this animate callback, which we write as a curly brace in Swift, we just imperatively mutate the state of our view. So here we just are changing the button to blue, and we're changing the X position to 4. And essentially, this gets animated in parallel and by the runtime. And then if you want to do something afterwards, to run something in sequence, you pass another callback. And Swift has this like crazy thing, this trailing closure syntax, where you can just open curly brace, close curly brace, and it's implicitly passed as the last parameter to your function. So to sequence two animations, we would, in the callback, animate again. So if we look at this, it's expressive enough because there are many iOS engineers who put animations in their apps, and they seem to get it done. So that's good. But I would say this is maybe a little bit complex in the sense that you need to know all these overloads. There's a bunch of hidden state. It's very imperative, et cetera. If we look at Android, this is sort of obviously complex, I think. So right here, I'm scrolling through the documentation of the animation, or how you're supposed to animate in Android. And I did confirm with an Android engineer who's currently doing Android. This is the thing you're supposed to use. It's like insane how many methods there are and how much stuff there is you have to think about in order to build any sort of animation. So if we think about our goals, it would be nice if we could actually get something that was simple but still expressive enough to do something interesting. I guess I'm just going to assert this, and I'll kind of motivate it. I would say composable APIs are ones that are expressive and simple. What is a composable API? Well, if you have some type, and you perform an operation on that type, and it gives you back that same type, we say it's composable. But why is this good? Well, we can take that result and sort of feed it back into the original operation and get new behavior. And so in one simple function, we can sort of get tons of behavior out of it, tons of expressivity, expressive power. So this is sort of the motivation. And by my definition of complexity, it's simpler because there's less you have to look at when you look at the API. So if we think in the context of animations, you can imagine maybe we provide a way to build complex structures out of Lego bricks. I guess that's the metaphor. Like we have a green brick, a red brick, and from those we can build walls and houses and castles and rockets. Okay? So keep that in mind. Okay, this notion of composition is something that we want. How do we find it in the space of animations, in this like abstract notion of an animation in our heads? I found 3 places where composition sort of comes up. So I want to talk about those. Okay, so cool. Okay, we can grow a circle. Think of that as an animation, right? We can fade out. That's an animation. If I grow and then fade out, then we can say that is a new animation, all right? So what you're seeing is like one animation that's composed out of 2, okay? And I guess I should say, for the purposes of this talk, my animation library is going to be one in which you cannot interact with. So it's just something that you you build up your choreographed little scene, and then it runs, and we can view it, okay? So anyway, this is the first form of composition that we find. Another is running the two animations in parallel. Okay? This is the same two animations, growing and fading out, but we're running them at the same time, and we get something that looks visually different if we actually do it, or if we think about it in our heads. It looks different, seems different, so it's different. You know? I'm going to denote this with plus for reasons that you'll soon see. Another form of composition is to change how time is perceived, and we use this to manipulate our easing curves. Okay, so the way I want you to think about this is, let's say time just marches on. 1 second of time in animation space happens in 1 second of time in real world space. Then we just sort of get a linear animation, but we can stretch out time in the beginning, squeeze it in the middle, and stretch it out at the end, and we get an easing curve, which is quite cool. So yeah, just to summarize, we can sequence animations, we can run them at the same time, and we can change the perception of time. This third one, I'm not going to have time to really dive into too much, but I just want you to know that it's there. So what do we do now? Okay, we've come up with these places where animations seem like they can compose with one another. And you could stop here and like build out a library. And if you try and write pure code, you'd probably make something that was quite good. But maybe you wouldn't. Like maybe you're having a bad day. Who's to say what's going on, right? And wouldn't it be nice if there was something that could guide you to the sort of best implementation? And I argue that there is something, and it's called math. We can do more thinking up front, and we can learn about the design of our code before we even start programming, before we even write down the type, if we just think about it sort of abstractly and mathematically. And then the question is, what branch of mathematics do you use? And you could use category theory, and a lot of people do, and a lot of people in this room probably do. But in certain programming languages, category theory is really hard to express. And Swift is one of those languages. So it's also hard to understand for new people, I would say, category theory is. So we're going to use a different branch of mathematics to help guide us, and that is abstract algebra. And that leads us to the title slide, 14 minutes in or whatever. So okay, I'm talking about abstract algebra-driven design. Hopefully I've motivated that enough. And specifically, we're going to use animation as our example. I'm going to show it to you in Swift, and I'm going to show you how it forms what's known as a semiring. And by the end of this, even if you start from nothing, you will understand semirings, hopefully. Okay? So this is the part at which I'm going to start teaching some really basic abstract algebra stuff. So to start, there's this notion of a binary operation. Okay? A lot of people write this with a diamond, but I'm going to use multiplication because it makes more sense in the domain of sequencing animations, I think. So bear with me. In Swift, we can actually just write a function on this operator like so. And here, we have a left-hand side, a right-hand side, and it returns a value. And you can implement this for all sorts of operations. We're going to talk about how it applies to animations, and specifically sequencing at first. So again, we already talked about this. If we grow and then fade out, we can sequence them together with this star operator if we implement this function properly, and make something like this. Okay? So at this point, I guess what's the point? The point is we can give it more meaning, and that meaning will help us in our implementation. It'll help gain expressive power for the consumers of our API. And we can do so using laws. Okay? What is a law? A law is an equivalence between two programs that should always be true no matter what. All right? So I'm going to talk about a few laws over this single operation: associativity, identity, annihilation, and commutativity. Okay? Cool. Associativity. All right. If you remember from high school, if you have three integers, let's just call it x, y, and z, and we add them together, it doesn't matter if you parenthesize the x and the y or the y and the z. You get the same result. Okay? And I showed this with 1, 2, and 3, but importantly, this holds for all integers no matter what you choose for x, y, and z. And because of this, we say integers under addition are associative. Okay? But what's cool, what I find really interesting, is we can just swap the math for a program. And we say, if I have a program on the left where I have x times y and then times z, and a program on the right, x times y, x times the quantity y times z, and I have this sort of equivalence that holds for any x, y, and z of the type that I've implemented this star operator for. Then we say that that operation is associative, okay? And you know, mathematicians have a name for this, and they call it a semigroup. This is the definition in Swift. If you've ever heard of the term semigroup, this is what it is. It's a binary operation with associativity, and you're not crashing and stuff. But I guess minor Swift break protocol, translate that in your head to interface or trait, whatever you like. And then this is how we declare that you must implement the star operator when you implement the protocol with a concrete type. OK, and then laws, we just write as comments. OK, so if we think about this in the context of animations, well, we use our imagination again, which I've happened to have rendered to this slide. And we can pick 3 animations out of thin air arbitrarily. Let's say growing, turning red, and then fading out. OK? And if we think to ourselves, doesn't it make sense if I'm going to run all these 3 things in sequence, it doesn't really matter if I parenthesize the first 2 or the second 2. The results should look the same. OK? And because of this, we kind of know when we're implementing it, if we implement this operation, it better be the case that the star works in this way. Sorry, I just realized it's cut off. I hope it's not cut off for all the slides, but hopefully you get the idea. OK, does that kind of make sense so far? So at this point, you all, for those that haven't seen this before, you should be thinking to yourselves, like, I don't care about any of this. What is this stupid math? I didn't get anything, OK? Yeah, maybe we did get one thing here that'll help us in our implementation. But as a consumer of the API, how is this making my API more expressive? How do I have more power when I use this API that happens to have an operation that's associative? And I would say you do get power. You get this freedom to chunk up work however you'd like as a consumer of this API. So for example, we could translate and then fade, and then store that in a variable, or put it in a helper function, or put it in a different library, and then later sequence it with a peer. Or we could inline it and do it all in one line. And this choice is for the person using your API. So by my definition of expressivity, it's more expressive. Okay? So as a corollary to this, and it's not something that's so useful in the domain of animations, but I really want to point it out. If you know your operation is associative, you know you can parallelize. So if you have 4 pieces of work, then you can choose to execute the first 2 on one thread and the second 2 on another thread. And if that work is really expensive, you've effectively doubled your performance. At the end, you have to combine them on some other thread. But so that's kind of cool, I think. OK, let's look at another law, identity, specifically the left-right identity. And what this says is if I have an empty element, and with integers, let's say 0, and I'm going to add x. Let's say I'm going to add an integer x to 0. What do we get back? X. Okay? 0, when you add 0 to anything, you don't change the thing you're adding to. So here's an example here. 0 plus 1 is 1. 1 plus 0 is 1. It's sort of not clear to some people like why we care about having an identity. And so hopefully I can kind of motivate that. This is the power you get when you have an identity. You can do something, maybe. So like, for example, if a user won, we could do an animation. But if a user didn't win, then we can do nothing. And this do nothing is captured in a value. And then we have this other value that we can use in a more complex animation. And again, it's up to the client. They could inline this, but they don't have to. So what do mathematicians call this thing, or functional programmers? This is called a monoid. In Swift, we say protocol monoid inherits from the protocol semigroup, which means it demands the things that semigroup demands. It also demands that you supply an empty element, and this is how you magically say that in Swift. And to implement a monoid, you must guarantee that you obey this identity law as well as associativity. So, OK, let's actually be more concrete here. if we have some animation like growing, what could be an animation that could behave as our identity under this sequential composition? And this, again, it's kind of like we think a bit, but here's what I came up with. Okay, if you have a notion of duration inside your animation structure, then we could say an animation of duration 0 that doesn't do anything in 0 seconds. We can stick that on the front or the end of any other animation, and it doesn't change what the animation looks like. Okay? So, and I'll call this the trivial animation. So the trivial animation is our empty with respect to sequential composition. Okay. All right, annihilation. What is annihilation? Annihilation is best expressed with integers. Again, if I have x, that is an integer, and I multiply it by 0, I get back 0, either on the right or the left. And specifically, what's cool about annihilation, it erases information. So I could build up a crazy animation, and if I have some annihilator element, some 0, I can just smack that on at the end, and what does the user see? Nothing. Okay? So again, this is, maybe you have a complex animation. If the user won, if they lost, you don't want to show them anything. So you slap on a 0. If we think concretely, like what could this notion of 0 be? I would say a canceled animation. Okay, so let's just pretend we have some notion of a canceled animation. If we have a canceled animation and we compose it sequentially on the front or the end, we say the result is canceled. Okay, and all these things, this canceling, the trivial animation, this is sort of giving us hints for when we actually implement the code of what we should do, what we should be looking for. Okay, last one, commutativity. What does commutativity say? It says x plus y is the same as y plus x. If you have that, then your addition is commutative. Mathematicians got a bit lazy, and if you have a monoid, that is, you have the identity and associativity. I say nothing about annihilation here. Bear with me. But if you have identity and associativity, and you also have commutativity, then you have a commutative monoid. Okay? Now, if we think about sequencing animations, just bear with me for a second. Recall. That's so weird. Nothing's showing up, but it's showing up on my computer.
It's been annihilated.
It's been annihilated. Here's my notes. Ignore that. OK, recall. If we grow and then fade, right, it looks like that. Now, hopefully the next slide's good. Yes, OK. But if we fade and then grow, we don't see the grow, because we've already faded out, right? So this means this sequencing operation is not commutative. When we implement it, it better be the case that it's not commutative. Okay, so this is another hint to help us in our implementation. What about parallel composition? If we think about that, if we think about fading and growing at the same time, isn't that the same thing as growing and fading at the same time, right? So I would say it's commutative. Okay, so when we implement this operation, we better make sure that this parallel composition is commutative. And now we say, OK, is it also a monoid? So is it also associative? Is it also a semigroup? It's cut off, but hopefully you can see. If we grow and turn red and fade at the same time, it doesn't matter if we parenthesize the first two or the second two. We're doing them all at the same time in the end. So the resulting animation should look the same. OK, is it a monoid? So that means what is the identity? And I'm picking the canceled animation to be the identity for reasons that you'll see. But it does make sense, right? Like, if I have a canceled animation running in parallel with anything else, I expect to just see the thing that was running. OK? So this canceling only happens when you sequence. OK, cool. So because it's a monoid, because it's commutative, parallel composition forms a commutative monoid in our land of animations, all right? Which is pretty cool. So what do we talk about? Associativity gives you the semigroup, and it gives you the power to chunk up work and to do things in parallel. Identity gives you the monoid if you also have associativity. And this gives you the power to like conditionally capture effects. And that's cool. Annihilation, we didn't talk about the structure, but what this lets you do is it lets you erase information. And then commutativity gives you a commutative monoid. And I didn't talk about this, but not having to care about the order is sort of, gives you more ways to solve the problems. There are more laws over a single operation, such as idempotence, but we don't have time for that. There is one more thing I want to think about, though, which is to consider how sequence interacts with parallel. Whenever you have two operations going on, you kind of want to know how they interact with each other. And there's sort of this interesting law that people think about a lot called distributivity, which you, again, may recall from high school, which says, let's think about integers, OK? If I have x times the quantity y plus z, that's the same as x times y plus x times z, OK? And we learned this in high school. But it's also true if you do the multiplication on the right. So if I have the quantity y plus z, and I multiply by x, it's the same as y times x plus z times x. All right? And here's an example if you don't believe me. But importantly, it holds for all integers. OK? And again, we do the substitution. And now we say, what does it mean for two programs to have this equality? And what power would you get? Well, this is cool. You can optimize. OK? So think about it this way. The consumer of your API decides it's more clear for them to write down x times z plus x times y plus x times z. And why stop them? Let them write clean code. But when we execute it, we want to be efficient. So what we can do is we can factor out the x. And if you count the total amount of work being done, on the left, we do 3 operations, 2 multiplies and an add. And on the right, we do 1 multiply and 1 add. So we've optimized. It's pretty cool. OK, let's actually think about our sequencing in parallel. And hopefully, you can read it just from half the text, since it's cut off. But so this is we're growing, and then we are turning red and fading at the same time. OK? And I would say, if you think about it, this really should be the same as growing and then turning red, run in parallel with growing and then fading. OK? If there is something weird here, if you believe that if I grow and grow in parallel, that it should look the same as just growing once. And now we have another thing that's sort of helping us guide our API design, right? And so I think this makes sense. If I say, hey, I want to grow to this big, and I want to grow to this big, and I do that at the same time, well, I want it to grow to that big. If I happen to say I want to grow a little bit, and I also want to grow a lot, and I run those at the same time, I think I want to grow to the average. OK? So think about if you do the same thing in parallel, we average the results. I think that's like a natural thing to do. And if we do that, then this holds. OK. We also need to look at the other side. So here we're growing and turning red, and then we're fading out. And again, the distributive law does hold as long as we say that, OK, fading out, if we do that in parallel, it means the same thing. OK. So now I can define semiring. Finally. All right. Here's the definition in Swift. A semiring is something where you've provided an addition operation, a multiplication operation, a 0 and a 1, such that plus forms a commutative monoid when you take the empty element to be 0, times forms a monoid when you take the empty element to be 1, times distributes over plus on the left and the right, and 0 is an annihilator with respect to the multiplication. OK? And since I showed you all of those things with animations, if we take times to be sequence and plus to be parallel, then animations are semirings. Whoa. Crazy. OK. I find that mind-blowing, personally. Because like mathematicians made this semiring thing when they were just trying to think about numbers and like maybe matrices, whatever. But this is an animation. Wow. That's cool. OK. So animations are semirings. Now we can think about the implementation. OK. Now that we've figured out the structure, we figured out something that's very nice and has all these laws. And we have this abstract model in our head. We know how it behaves. We know the expressive power that our consumers will get if we provide such a library. This is good. OK. And now we use creativity. But we have these guide rails that sort of point us in the right direction. At this point, in the context of this animation library that I actually worked on, I sat down with two very smart people, and we tried to make this a reality. Specifically, I just want to name them Chris Eidhoff and Brandon Williams. So thank you to both of them. We played with a bunch of different representations until we found one that seemed to be really nice and actually was a semiring. So let me just get a drink, and then I will show you. OK, are you ready? What is an animation, really? I would say it's a value that changes over time. OK? We can choose to render this value to the screen of our iPhone. OK? We can choose to render it to a web browser. We can choose to render it to standard out. And if you see raining text, that's kind of an animation, right? So really, a value changing over time should capture all of that. But this is not a rich enough definition to capture the things that we learned when we were going through the abstract algebra. So I'm going to enrich this definition a bit. What is an animation? An animation is either a value that changes over time coupled with a non-zero duration. Remember, we said we needed that duration. I'm going to say non-zero because we're going to divide by it at some point. Or it's a canceled animation, which is our additive identity, or it's a trivial animation with no duration, which is our multiplicative identity. OK? So now that we have this description in our heads, we can sort of trivially convert this into source code using the algebra of data types and parametricity. A value turns into A. OK? And in Swift, we use enums to do this. But think of this as like a data type or a case class. OK? So we have a canceled animation, or a trivial animation, or a runnable animation. And if it's runnable, we have a duration. And we have a function that takes a progress between 0 and 1 inclusive and produces an A when you give it a certain percentage of the way done that the animation is. And this is how we capture the value changing over time. OK? That's the type. Now we implement the protocol. OK? I'm going to show you the entire source code. So it's like not long. OK. Animation is a semiring. So what is the multiplicative identity? It's the trivial animation. We already talked about that. What is the additive identity? The 0. It's the canceled animation. We already talked about that. OK. What is sequential composition? So I have two animations. I'm returning an animation. In Swift, when we want a pattern match, we use the switch statement. And OK, if one of those is canceled, we said cancel annihilates over sequence. So we're going to return canceled. If one of them is trivial, we return the other one, because trivial is our sequential identity. And then the interesting case, I have two runnable animations. So I have two durations and two value functions. The total duration is going to be the sum of the two. Like if we take a short one and a long one and put them next to each other, we run for the total time. And then we want to get the ratio of how much of the first one are we in this total time. And that's that ratio line. And then we can return a new runnable animation with the duration being the sum of the two. And then we use this neat Swift syntactic sugar for supplying the function as the last argument with just a curly brace. OK, think of this as the argument to the runnable constructor. All right. So t is this number that ranges between 0 and 1. So now we check, is it less than the ratio? If so, use the first value function. Otherwise, use the second value function. And we divide and minus to sort of get us back into the domain of 0 to 1. OK, that's the whole thing for sequential composition. Parallel composition. Turns out, if we run two animations in parallel, like I said before, we have to figure out how to combine the two. You can argue with me if this was the right choice, but I said, hey, if you have a commutative semigroup, so you have commutativity and associativity, then I'll combine them, sure. Concretely, we're going to use average for this, all right, in like most cases. So what is parallel composition? it's addition. I take two animations. I return a new animation. Now we switch. OK, if one of them's canceled and one of them's trivial, or if they're both trivial, I'll just return trivial. This is a little bit arbitrary. I think this kind of makes sense because 0 plus 1 is 1 in integers. So canceled plus trivial should be trivial and not canceled. But bear with me. If both are canceled, the result will be canceled. And then the interesting case, I have two runnable animations, two durations, and two value functions. I have a new duration, which is the max of the two. OK? And then now we have to think, OK, what if one of them was shorter than the other? We want the resulting animation to execute for the full time. That's why we take the max. But we need to do something with this shorter one. And so what I propose is let's the animation runs, and then it just freezes at its last state and hangs that way for the rest of the animation. OK? So that's what we'll do. We return a runnable animation that is the max of the durations. And the value function calls both of them, but it does this min1 to clamp at the end. OK? And then adjusts based on the ratio. And then we have two A's, and so we have to combine them together. And that's where the commutative semigroup thing comes in. Think of that combining as taking the arithmetic mean or the average of the two values. And there's one more case. If one animation is runnable and the other is anything else in the parallel universe, in the universe of parallel composition, we say we just see the runnable animation. OK? That's it. That's the library, basically. So now, of course, we want to validate our laws. Like we said all these things should hold, and we implemented this protocol, so we better make sure that we actually did the right stuff. There's a couple ways you can do this. One, you could just try a bunch of examples in a REPL. This is not the best thing to do, but it's something. Here's a screenshot of that. You could use property-based testing to try and generate counterexamples. Or you can use a formal proof if you're really crazy. But we're at LambdaConf. OK. So obviously, there's like a few other things in the library that I didn't mention. I guess I'm going to mention one of them. We want this notion of mapping over an animation. So like, we're going to construct animations that just change floating point numbers. And at some point, we want to take those floating point numbers and change a view so that the animation actually does something. So here we're mapping a floating point number into the radius of the circle as it goes from 0 to 200 with some specific easing curve. OK, so that's basically it at the core, right? But what's really cool, OK, if you build libraries like this, and this doesn't just work for animations, if you do any sort of library in this way, you can provide layers of functionality. So there's layer 1 is what we talked about. There's this notion of like a layer 2 primitive, OK? And that is all of the things that I'm going to show here, and many more that I won't show, can be built out of the core stuff that we wrote before. And actually, everything, all other animations, the whole thing will be built out of just the stuff that we saw before, just the multiplication, addition, 0, and 1. That is rich enough to describe all animations that sort of run, as long as you don't, they're not interactive. I will assert that, and let's talk about it later if you disagree. But using that core layer, we can build things that are really useful for people. So one is, how much time do I have? OK, cool. One is if we have an animation and we want to actually get the reverse, we can just have a reversed property that gives us a new animation that runs backwards. And the implementation of that is just 1 minus the result of calling the function. We can have an animation that loops, that is, play yourself and then sequentially compose that with the reverse of yourself. We can have an animation that's delayed by some constant time, where we'll just have it freeze, as I am doing. We'll have it freeze at the beginning, and then hang for a bit, and then start. OK? Or this is a very useful one. We can linearly interpolate from a starting point to an ending point in floating point numbers over a certain duration, and get back an animation of floating point numbers that when you combine them in parallel, they average. That was a mouthful. But this is like a super useful primitive that I use all over the place. And you can go on and on and on. And these are the things that you would want to provide in the library, I would argue. But then what's really cool is there's this notion of a layer 3 primitive now, where pretend you're at some big company, big corporation, and you have a team of engineers, or your core infrastructure engineers for your application, and they work closely with the designers, and they say, okay, this is the fade out for our product at corporation X, and we need the fade out to have this specific easing curve and last this long everywhere it's used. And we have a translate that has this specific easing curve and lasts for this long. And we have a rotate that rotates this many degrees because corporation demands it. And then your product engineers, the ones that are actually building out the features, then just use these layer 3 primitives, and they'll create something that is to spec for your company's style guide, which I find really cool. So okay, what's the point? Well, now we can build up really crazy animations, and in my creativity, here's my really crazy animation. So I have 3 views. One of them is growing, and then the other one's fading in at the same time, and then we fade out the blue, and then we fade in the green, and the fade in's faster than the rotation. Hopefully you can use your imagination and see how you can build really like anything from this. That's probably a visualization error. And in fact, that's a good segue. OK, that's a bug that's my fault. But speaking of the visualization, OK, so what have you seen on these slides, right? I've showed you animations to try and teach things, OK? And on the bottom, I showed this timeline view. And as the animation's happening, we see the timeline filled out, except for the bug I have at the end there. But so how did I make this, OK? So this is my argument for how you can build interesting things if you build your library in this way. I made a system for describing animation scenes over a specific set of actors. In this case, the actors are the circle, the red square, and the green square. It'll position them in the center of your canvas, and then it'll draw this timeline view for you and animate the timeline view to help illustrate what the animation is doing. And the only reason I was able to build this without maybe being too upset at how difficult it was is because the animations were structured in this really nice way. They have this semiring structure. And clearly I made a mistake. But I didn't make a mistake in where the intervals were. I only made a mistake in the drawing code. And that is like annoying boilerplate that you just have to use the vendor's APIs.
See, by the way, I thought you didn't because I thought that your math actually, I think, is to do exactly what you're doing right there. But I think that's just the math you end up picking for your how do you get the 2 to go at the same time.
Yeah, I probably did that wrong. But cool. Yeah. So how did I do this? Well, basically, I have this intervals function that takes a description of the animation as a semiring. And in fact, it's a free semiring in this case, which if you were in the free talk, maybe you know what that is. I don't want to get into it. But from that, in 15 lines of code, which I have in the appendix, maybe it's 18, something like that, I can give you back a list of labeled intervals that tell you where you need to draw the things, where you need to draw each section of the timeline in the full scene. In 15 lines. I mean, come on, that's crazy. And then there's annoying drawing code because those APIs aren't nice and composable, so it's quite annoying, at least on iOS. And what you're seeing actually are videos that were rendered in an iOS simulator using the library I wrote for building animations for iOS. So like the actual MP4 compositing happens in an iPhone simulator. So this is the real library. I guess I just want to say that. OK, what should you take away? Remember, sorry, API design is about maximizing simplicity and expressivity. OK? And my notion of simplicity is you don't have to think about things in the interface. Yeah, you have to know what a monoid is. But if you know what a monoid is, you know what it is for all libraries. It's not something specific you have to learn for animations. OK? So I'd say it's simple. And it's expressive. It's expressive enough to build any sort of arbitrary animation. I don't know if hopefully I motivated that enough. And you can build the cool timeline view. Composable APIs maximize these properties, I would say. And we can find composition in animations. And moreover, if you're building any sort of library, I think it helps if most of the time you can find some form of composition if you think really hard. But you shouldn't stop at composition. You should really think about the laws. And the more laws you conform to, the more expressivity you give to the consumers of your API. And that's why we care about laws. That's one reason anyway. But it also helps you in your implementation of your actual code later. And then these libraries empower the API consumers to do amazing things, like build layered architecture of APIs, of animations, or construct a timeline view automatically from a description of an animation. So with that, I will end. So this is the talk. That's my name. That's my Twitter. There's an underscore at the end. That's a link to the library and a link to the slide deck. And I guess if we have time, we have I guess I should take questions, but I just want to show. Hopefully, this is a little bit crashy, especially when you have an external monitor plugged in, but I just want to show. This is like a live preview of, OK, so I made this circle really big for the purposes of seeing what's going on. I don't have a mirrored thing, but that says 500, right? I can change this to 100. By the way, this is running in an iPhone simulator, OK, on my computer. And it's 60 FPS on a phone. It might be a bit laggy on the computer, but you'll have to take my thing. But yeah, I just changed it to 100. Anyway, so you can kind of get the idea, hopefully. So cool. Yeah, turn off. All right, I'm going to go back to the slide. OK, so I guess I can take questions for 2 minutes.
Really good talk and really interesting structure. I'm a little bit surprised to hear you say that the primitive of averaging together, let's say mutually conflicting or overlapping animations, that you found that eminently useful, because in my mind what that does is the thing you don't want, which is even if you have two continuous and C1, C2 continuous animations, so their derivatives are continuous as well, if they overlap, you lose all continuity in the edges. So let's say you have something that's fading out and then fading back in, and you overlap the fade out and the fade in.
Yeah, OK, you're totally right. You know what it should do? Thank you for saying that. OK, I should change this, actually. Cool. There's this thing. This is probably what you were getting at, but maybe I'm sure you've seen it before. I mean, I've talked to you. You know your animations. But there's this thing. I don't have internet. There's a thing called additive animations, and that's probably what you want. Or something like that. Anyway, you're right. Averaging is probably the wrong thing. But
well, what you want is basically insert an animation of the transition in the overlap. Right?
OK.
So that you do a crossfade between the two animations that is itself also eased. So that way you retain not just continuity, but derivative continuity. So it's
interesting.
Do you lose monoidity then? Would you have to understand that application?
It depends. If your animation primitive can give you a value as well as a derivative,
yeah,
just the value,
then
you can
interesting.
construct the intermediate animations blindly. But I think if you only have the value, then
yeah, that's cool. All right, go ahead.
If you needed to tackle the same problem, but for simple 3D animations, would you expand on this library or create it?
I think you know who you should ask, but I think this core semiring type structure, maybe you also want the derivative, but I feel like this core you should be able to use to build out an animation library that should work for arbitrary dimensions.
yeah,
right?
Animation is by itself a very composable problem. And one thing that I'm kind of interested to hear if you want to explore this is you can treat a presentation, a PowerPoint, as a regularly stepped animation, but with a controllable playhead.
Yeah.
You're sort of scrubbing forward in time as you go to the next
right.
slide and then stop. So by
That's cool.
These kind of constructs, you can do a lot more than you might think
That's
at first.
Mm-hmm.
And 3D, 4D animation is all the same.
Yeah, so it's really, and actually just one thing I should say, I didn't talk about the runtime, but obviously you need something that was very side effecty and whatever to actually consume this function and call it over time and to actually do something. So for example, you can ask your operating system to call it every frame, or you can, if you're rendering to a video, you can call it when you're ready for the next frame to render. But yeah, question?
Yeah, the question is, so you were talking mostly about non-interactive?
Yes. What about
So when you go to interactive
Yeah.
animations,
what do you do?
the structure Oh,
Yeah.
suppose it
I think so. I haven't thought about this enough. Chris Eidhoff, one of my collaborators, was thinking about this. I wasn't sure where he ended up with. Like, I think you need a notion of a like an FRP type stream or behavior, whatever you want to call it, in order to capture interactivity. But so I don't know if you can get something quite as nice without either like saying, okay, let's just have side effects, or introducing this like sort of extra complexity. But it's not something that I've thought about enough. It is an interesting, it's an obvious like addition that should be thought about.
Use this technique like in production and applications that you've written? Do they have interactions?
Yeah.
Or did it not
Well, yeah, so right now I'm not actually working on apps, so I haven't used it in production, but I used to. But the way I imagine this could be used is one in like very beautiful presentations, like if you check out acco.net, you know, although yours are interactive, so I shouldn't say that. But also like splash screens and even like loading indicators. In many apps, you know, if you scroll to the top, you see like a dancing bear and a balloon and juggling and all this crazy stuff. And I think that can be expressed really, really nicely as just a bunch of primitive things that you're running in parallel or sequence. Oh, and one thing I should mention, the nice thing about this construction, we have like a floating point value that changes over time. And we can then sort of map that to a particular view, but we can reuse that same description of an animation and compose that together with a bunch of stuff, and then apply it to several different views, like actual concrete things on the screen. We can use the same curves, and et cetera. So it's like super, super composable. And every form of composition gives you more expressive power, and that's good.
Thank you.
Cool. Any last questions? Yeah.
So it seems like you talk about how it's a semiring with plus and multiplication, but time is almost like pasted on. Is there some way to think about time mathematically or with abstract algebra?
Yeah.
So it's not just like an out-of-band additional thing.
Probably. So the duration is captured in there. I think it's kind of nice to think of like a value changing over time. If you think of anything changing, it's nice to think about that as a function where you supply the sort of, hey, you should change in this way thing. And so I think it's kind of nice to say a value changing over time is a function from the current time to whatever the value is. But I don't know, maybe there's other ways to do it.
Just wondering more like at the abstract algebra level.
I see.
I'm not sure. But
Yeah, I'm not sure either.
has anybody applied time with abstract algebra? Okay. Cool.
Cool. Any more? All right, thank you.